I'm Tim Ventura from AmericanAntiGravity.com, and I'm speaking today with Dr. Dennis Bushnell, Chief Scientist at NASA Langley Research Center, and we're talking about space. Well, Dennis, I appreciate you joining me, and I'd like to start out by asking about the National Space Exploration Vision and how that relates to human expeditions to Mars. With all of the financial and economic upheaval that we've seen over the last few years, do you think Mars is still a definite yes for NASA?
Mars is a definite yes, but it's not if but when. And to do Mars both safely and affordably, because currently with the technologies we have, the usual outlook is what's safe is not affordable and what's affordable is not safe. So what we're trying to do is to ideate technologies which would reduce the cost sufficiently so that we could afford the right safety, and then we could go. And the estimates are it would take us about 15 years to work through the research, another 15 years to do the development, and so we're 30 years out to Mars.
Now, you had sent me some stuff to read through as preparation. The document that I'm looking at here is Advanced to Revolutionary Space Technology Options, the Responsibly Imaginable. Now, I went through this very closely last night, and one thing that jumped out at me was the possibility of hexavalent chromium making the Martian soil and atmosphere poisonous. Can you tell me a little bit more about this?
My understanding is that hexavalent chromium, which is an industrial chemical, is the most potent carcinogen known. Very trace amounts of it, produces cancer. And so, if we go to Mars, if that stuff is there, and it appears to be there, then we're going to have to go dust-free, and that includes dust-free for HABs, for transport vehicles, for suits, for everything. This is not simple to do, to go dust-free.
Well, do you think that's achievable, to be able to completely reduce the dust? And I've read a little bit in the preparation I did. It looked like they were talking about being able to take it down to trace amounts below the carcinogenic threshold.
Yeah, the carcinogenic threshold is at least parts per billion, and I don't think anybody's sure whether parts per trillion would do it. You can take it down that far. It's just a matter of engineering craftiness, invention, and cost. You've covered so far the hexavalent chromium, which is not really the major health issue. The major health issues are the partial G. We don't really know how much G decimates the immune system. We know micro G decimates the immune system. And then there's the radiation. Mars, except for very locally, has very little magnetic field. It's very different from Earth and has very little atmosphere. So you're subjected to about 80% of the 30 to 50 giga-electron volts of iron nuclei from the galactic space radiation. And this, of course, is carcinogenesis to a great extent, as well as it also decimates the immune system. One reason to terraform is to melt the water, which is under the CO2 at the poles, and there's enough there to put a shallow ocean on a planet, and then we could add bio and produce some oxygen to get some oxygen to breathe, as well as get some density into the atmosphere so that we could have some kind of protection from the radiation.
Isn't the planetary mass kind of an issue with that on Mars, though? If we do eventually pursue some kind of terraforming, is it always going to be an issue with having that atmosphere slowly boil off?
Yeah, it is. But if we can convert the soil into atmosphere, into oxygen, which is what the plants do, plants for planets. With the genomic and synthetic biology, the extremophile business, we can probably produce it about as fast or faster than it boils off.
Well, now, in terms of the radiation, in more near-term exploration, one of the things that you'd cited was the possibility of DNA self-repair, and that potentially there might be some research that could basically advance healing times for astronauts, right?
Yeah, What you want is a DNA repair, which is faster than the radiation coming in, altering it in bad ways. About 12 years ago, there was some genomic research up in the Boston area where they were able to develop treatments, genomic treatments for people undergoing radiation therapy for cancer to protect the tissue, which is not cancer cells. But that's at radiation levels, those are therapeutic radiation levels, which are far less than galactic space radiation by many orders of magnitude. The extent to which we can do this for very high radiation levels, we're actually doing some research here on that, and it looks like there may be some partial success so far.
I think that's really valuable because a lot of people forget once you start getting out past Mars, you get out towards Jupiter, don't those radiation levels jump way up?
I think they're pretty much what it depends. There are two types of radiation. There's the solar particle events, and then there's the galactic space radiation. And the galactic space radiation is pretty uniform. And that's the high Z stuff. This is the really high energy. The solar particle events would reduce going out, but those are very episodic and actually easier to protect from.
Oh, okay. Because I'd heard that Jupiter actually created radiation of its own.
Jupiter does, but it's a different kind of radiation entirely.
Oh, okay. Well, now, the other aspect of this is the cost of space travel. And you'd written about this, especially the cost in terms of man-rated systems. It seems like cost-effective solutions aren't in the near term, but there are a lot of options farther out.
Well, one thing which we need is a transportation system which would get us fast transits, because fast transits have all kinds of benefits in terms of cost, in terms of psychological benefits, in terms of health benefits, and so forth. Chemical is probably not going to be doable because of these many favorable effects from much faster transients. The Vasimer propulsion system looks interesting. This is a high-thrust MHD device, but it requires a lot of energy. And so you're talking about large nuclear reactors, which have all their weight and so forth. There are a lot of future possibilities. There's antimatter, particularly anti-electrons, positrons, which look interesting. People are starting to store those as positronium. If we can store them, then those are 10 to the 9th times chemical. Conventional nuclear is 10 to the 7th. Then there's also low-energy nuclear reactions, which we're working on here. We've got 22 years now of experiments on low-energy nuclear reactions, which indicate out of hundreds of experiments that this is real. And we now have a theory from Martian that indicates that it's a condensed matter nuclear physics. It's collective effects. It is not particle physics. It is not the usual business, and you can get around the Coulomb barrier by forming ultra-weak neutrons using heavy electrons, which not only enable you to form the neutrons, but also convert the gamma radiation, which comes off of the beta decay, which is where the energy is finally produced, convert that into thermal so that you don't have to have much radiation protection. So LENR is expected to be anywhere from 20,000 to 3 million times chemical, and that would really revolutionize space.
Oh, okay. I didn't realize that LENR was being investigated that heavily by NASA.
Well, it's not heavily. I mean, we have a 200 to 300K a year effort. We're also cooperating with people that we can't divulge under cooperative agreements. There is quite amount of interest because the LENR purportedly also produces transmutations. So for in situ resource utilization, if LNR works, then we can take whatever's on the planet and possibly transmutate it into something we need.
To me, that's just so intriguing because Dr. Robert Bussard sold me on the Polywell reactor a few years ago, and so I'd always thought fusion would be the way that things would progress.
I'm very familiar with the Bussard stuff. That's an aneutronic fusion, p-boron 11 or deuterium helium 3, and that may be possible. It's yet another of 5 or 6 very advanced energetics technologies which we need to study much more heavily than we are now.
Yeah. I just read about the 100-year Starship program, and to hear about the LENR work and some of the other advanced research that's going on, is NASA in some ways kind of going back to the drawing board and just looking at more advanced options?
Well, if you look at space access, it's essentially done today the way it was done in the 50s. These are ICBM militarized versions of German V-2 rockets. It's a chemical. We're out at the ragged edge of the performance of chemical rockets. And we need something a lot better than that if we're going to do safe and affordable. So, what we realized, NASA realized, is that if you're going to be able to do space exploration, particularly with humans, safe and affordable, you're going to need another whole level, another whole generation of technology. But back when the Bush era space program was launched, this was done with essentially conventional technology, and over the years, in many projects, NASA has learned that if you want to do revolutionary goals like humans to deep space, you need revolutionary technologies, and to the extent that these are not cheap to develop, we had to divert resources into space technology, which we're doing.
Yeah, and it sounds like some of the technologies that you've written about are almost mitigating factors, like some of the advanced launch technologies, where it may not necessarily help in space, but it definitely helps to get things into space.
Getting into space is a big part of getting to Mars, climbing out of the Earth gravity well. The in-space propulsion transfer is another 35%. The stuff to keep humans pink and warm, HABs and space vehicles, is about 25%, and the rest of it is the marching army. So getting to space is a really big deal.
If we go towards fusion rockets and things like that, those can't be used in the atmosphere either, can they?
Fusion rockets could, but particularly the aneutronic versions, and LENR could, if we get that. There are even assertions that at the one time people working on a nuclear rocket called Timberwind that they thought might be safe in the atmosphere, but other people are not so sure. But fission rockets are a problem in the atmosphere, but particularly aneutronic fusion rockets, maybe not. LENR, maybe not. Antimatter positrons, maybe not. And then there's one we haven't discussed, which is energy beaming. You can beam energy from the ground up to rectennas, and there's breakthrough rectennas thanks to nanotechnology. You take this off-board energy on board, and you can take conventional fuels. If you put some alkalines in them to get some conductivity, you can get like 2,000 to 2,500 seconds of ISP.
Would that be like the light craft?
No. The light craft is a different propulsion system entirely. The light craft has a problem with having net payload. This takes the energy on board and uses it to energize a high-thrust MHD device.
Oh, okay. So you're still burning fuel. You're just burning it in a different way.
Well, you are burning it, but of the 2,500 seconds, all right, you only get about 400 seconds from the burning the fuel. The rest of it comes from the off-board energy accelerating the what is now propulsive mass.
Well, now, in terms of the cost factor for this, another area that you'd written about was robot fabrication. And you'd said that the money isn't actually burned as fuel. The money goes to pay for people to build things. And if we're able to fabricate things expensively, then we can bring the cost down to get things into orbit.
It's far more than that. SpaceX, a lot of their cost reduction is that they have a really small launch crew with really small. I mean, for the shuttle. The marching army costs for the shuttle, people on the ground doing stuff, in between flights and everything else, and refurbishing, that was about 45 to 48% of the cost of a shuttle launch. So if you went and with the robotics we're now developing, particularly farther term, you can robotically design, fabricate, transport, erect, launch space vehicles without people.
Do you think that if we manufacture things in space, or if we manufactured spacecraft on the moon, do you think there'd be a significant cost savings by trying to do that too?
I have looked seriously into space commercialization, and we tried really hard to figure out how to commercialize space station. And we tried microgravity, we tried growing crystals and growing all kinds of stuff, and this is a push. There's not a lot of beyond the positional Earth utilities, okay, conventional space industry, telecom and weather and resources and that kind of stuff. But aside from positional high ground Earth utilities, manufacturing stuff in space currently is just very expensive.
Oh, because everything has to be adapted to work in that environment.
Well, and you got to get it up there.
That was something I'd wondered about, because I'd always read about how space mining could be so profitable, and then I thought, well, potentially we could utilize that in space as well.
Well, if it was that profitable, we would have been doing it a long time ago. Okay, we're still not doing it, and unless and until we can get the cost of space access down very appreciably, as far as I know, the business case doesn't close.
Let me go back to Mars for a second, because one of the reasons I asked about fusion a moment ago was you'd mentioned microgravity effects, and my impression had been that something like a fusion drive, you could basically accelerating halfway there, flipping the craft around, and then decelerating, but you'd still have 1G the whole time.
That's not very efficient. But what we're looking at, which may interest you, is regenerative aerobraking. This is where you accelerate out of the Earth's gravity well, coast, and then when you get toward Mars, as you slow down in the Martian atmosphere, you take the plasma, what you're producing at the front of the vehicle, run it through an MHD generator instead of an MHD accelerator, and you can take that energy and heat at lower altitudes CO2 that you bring in order to slow down. And you can store the energy on board, or you can beam it down and heat rocks and use it later. This is like regenerative braking in your automobile.
Yeah, actually, that is really interesting. Well, now, Sonny White recently published some calculations that seem like they might support this Alcubierre drive.
I suggest that anyone's interested in something like that they go to the Wikipedia page on the problems with physics. And there they will find out that at cosmological scales, we really don't know what's going on. We don't know what dark matter and dark energy are, which is 96% or so of what's out there. We don't know what it is. There is, between the cosmological constant and what quantum technology says, quantum science, some 108 orders of magnitude difference in energy level, We don't know what happened to the antimatter when the universe formed. Half of it was supposed to be antimatter. We don't know where it went. And this Wikipedia page is actually many pages, goes on and on. My conclusion from all of this is we don't understand physics at cosmological scales. And unless and until we do, it's not clear whether Sonny's assertions, which I'm very familiar with, or anybody else's assertions, will in fact get us anywhere. Most people who have looked at those drives say you need to produce massive amounts of negative matter and all kinds of other exotic stuff. Some people, there are people trying to work in various places on approaches to get that energy use down, but nobody has got anything defendable or believable at this point.
I see what you're saying. And so in terms of planning for things that we know will work, Alcubierre would be way too far out, and there's way too much unknown territory.
My hope is that if we ever do figure out what's really going on in physics at cosmological scales, that may inform us and enable us to go do faster than light, transportation, which is what you need if you're ever going to do anything outside the solar system.
Well, another area, and you had actually told me about this in a phone conversation several years ago, and you were talking about robot exploration, and I'd mentioned Ray Kurzweil to you, and you'd said that he'd spoken at NASA, and to me, the way that you described robots almost as kind of like the children of mankind really stuck with me, and it put what we're doing on Mars right now in a new perspective for me.
Well, that quote, robots being the children of mankind, is actually from Hans Moravec from Carnegie Mellon. He has various books on this. Robot is one of them from the early 00s, as I remember. And the idea is that we are currently becoming cyborgs at a very fast rate. The IBM Blue Brain project, which is nanosectioning the neocortex and replicating it in silicon, has made such good progress that they are claiming in 12 to 15 years they will be able to market a biomimetic human-level machine intelligence. The nano-functionalization of robots is continuing apace very rapidly. So there's no reason why in the 10, 20 year, 15 to 25 year out, that exploration can't be done very well with robots at a cost which has been estimated at about 1/1000th that of sending humans. So one way to do this exploration of Mars and so forth is three stages. One is to send the nanorobots and instrument the planet and send back the data. And the Brits demonstrated 5 senses virtual reality, haptic, taste, touch, smell, sight, and sound recently. So everyone could explore Mars anytime they wanted to at 1/1000th the cost of sending people. Then you send other robots to terraform Mars. And by the time that's done, we will have developed the energetics so that people could go, very inexpensively and very safely.
Well, and this would definitely get around radiation effects. It would get around the hexavalent chromium, depending on how those levels are. And then I'd also read that the Martian dust could potentially be highly caustic.
Well, it is. I mean, Mars is red for a very good reason. It's very oxidative.
Yeah, those are all sorts of things that, again, would interfere with people, but if it was a virtual environment, people could have that same experience. We could do more or less the same learning. I guess the question then is, does that diminish the achievement at all if robots do it instead of people?
Well, Tim, it's all in our head. Okay? I mean, the rest of the body is there so that we can get the head working. There's a generation coming up now that's used to living on electrons. People tell me that 5-year-old kids are out on the school playground texting each other across the playground instead of going over and talking to them. There are millions of people, many, many millions worldwide, who are spending more time on Second Life and other virtual worlds than they are in the physical world. Okay, we are in this IT age, and what's beyond the IT age is the virtual age, and we're going to the virtual age very, very fast. We are everything. We have some 48 million telecommuters, heading much higher. This is almost 1/3 of the workforce. We have teleshopping, which, by the way, uses a factor of 30 or so less energy, or less a climate effect. We have teleeducation, which is now taking over conventional education at much reduced cost. We have telemedicine. We have socialization. Telecommerce is endemic. I got a nice note from the IRS last year that said, please don't file in paper. This is where the world's going. So why is, space exploration so different?
Well, and it seems like, in a way, at least those basic steps are already underway. I mean, it seems like we already have a communications infrastructure in place. We have robots on the ground. We have probes orbiting it to repeat those signals. So it seems like those first steps are already underway in terms of robot colonization, if you will.
Oh, of course. But we need to get the robots smaller. Need to get the cost down so that we can, instead of just crawling around a couple hundred yards, we can instrument the planet.
Well, Dennis, we're almost out of time for today, but I want to thank you again for joining us and for sharing so much insight into NASA's latest research, especially in terms of low-energy nuclear reactions. It's been an honor to speak with you and a wonderful opportunity to share some really encouraging news with our audience.
Okay, Tim. It's an honor and a privilege. Thank you very much.
Thank you.